Today, I just wanted to go through basically an introduction to safety evaluation, which is pretty critical to a lot of the ongoing research that is being done broadly in our group. So Dr. Gates and I have done a lot of evaluation type studies where we're trying to basically assess how effective different types of crash countermeasures are. And there are a variety of methodological concerns that arise when we're dealing with crash data. And so we'll talk a little bit about that. From a big picture perspective, I'll talk about a few analytical frameworks that we commonly use. And then related to that, I'll have some practice problems and some more quantitative examples that I'll post subsequently. But this lecture is going to focus just kind of on the big picture of what we're doing conceptually and what the advantages, disadvantages, and limitations of some of these different methods are. Okay. And so specifically, we'll talk about project evaluation from a big picture perspective, and we'll talk about three different types of study designs. And so the first of those is just a naive before and after study. We'll talk about using before and after studies where we're also looking at reference data from a control group, and then we'll also talk about cross-sectional studies. And so I guess just to give me some sense of what background you may or may not have seen here, are you guys familiar with any of those three approaches to evaluation?
Yeah, I learned about the naive before after and then the control before and after in advanced highway design a little bit.
Okay. Did you get into any sample problems or things of that nature?
Yeah, and we also touched on empirical Bayes too, but I certainly could use more information about that.
Okay. And was that the cable barrier data set that you were using in that? Do you recall?
It sounds familiar. I believe so.
Okay. I just want to make sure I'm not just giving you the exact same data set that Dr. Gates has already used previously. So, okay. And then, Travis, you haven't seen any of this really previously?
Not
Okay.
yet, no.
Okay, sounds good. And then we'll conclude with just a few analytical concerns that we'll talk about in greater detail next week when we get into empirical Bayes and some of the more complex evaluation methods. So anyway, like I said, a very common scenario we run into in traffic safety is that we've applied a specific countermeasure and we'd like to know how effective that countermeasure is, and that information will be useful for several purposes, one of which we talked previously about how states are focusing more on performance-based evaluation and data-driven safety analysis. And so there are federal reporting requirements, for example, for the Highway Safety Improvement Program projects that are implemented around the state. And so states are required to monitor crash data, and typically they'll look at 3 years before and 3 years after those treatments are applied. And so part of it relates to just performance measures and evaluation. And then secondly, that also helps to inform where and when these treatments are applied, because sometimes some of these countermeasures work better at some locations than others. And we can get some insights to that as a part of our data analyses. And then also more broadly, oftentimes we'll have some pilot treatments that can be applied just to get a sense of how effective they may be when applied at larger scale. And so a good example there would be either the high tension median cable barrier or the centerline or shoulder rumble strips. And we had helped MDOT to evaluate both of those back in the early part 2010, 2011 time period. And so based on the results of those evaluations, we were able to help develop guidance for where the best candidate locations would be for subsequent installations based upon that evaluation that was conducted. Okay. And so when we talk about evaluation plans, there's a wide range of different methods, with the simplest of those being the ones that we'll cover today. So naive before and after studies, before and after with control groups, cross-sectional studies, which we'll also see referred to as comparative parallel studies. You might see a few other different nomenclature for that type of study design as well. And then we'll come back next week and talk about the empirical Bayes, which has become much more widely applied over the last 10 years or so, particularly. So So the simplest of these methods is just the simple naive before and after study. And so if we think about trying to evaluate how effective a countermeasure is, and we think about ways that are relatively straightforward and easy to do that, the naive before and after is the simplest type of evaluation here. And so all we're basically doing in this context is we're measuring how many crashes occur at a given location before we implement the countermeasure. We come back after the countermeasure has been implemented, and then just through a simple comparison of those pre and post countermeasure crashes, or we could look at various other metrics like the rate of crashes or the severity of crashes, but we're basically just making a comparison between whatever our performance measure is between that before period and the after period relative to when that treatment is applied. Okay. And so we generally refer to it, and it's, I guess, somewhat funny that we refer to it as naive before and after, because just the name kind of makes it sound like it's not a particularly good method. With that being said, a lot of states use this, and it gives us a reasonably good estimate in lieu of more complex statistical analysis of what the effectiveness of some of these countermeasures are. But the nomenclature there, naive, just refers to the fact that crashes from the pre-installation period are used to predict crashes during the after period. And we're not considering any other factors that may have affected safety between those two periods, besides just the fact that the treatment has been applied at that location. And so consequently, we're making a number of simplifying assumptions. As a consequence, the math is really easy, but there are some concerns in terms of how reliable those estimates would be. And if we were to take the results from a before and after study and try to use it to forecast what type of performance we'd see if we implemented that countermeasure at a different location, we'd likely find in many circumstances that we'd see some differences. Okay. And so if we think about this in context, so we've got some performance measure of interest. Typically, we're talking about the number of crashes, for example, here. And so in a naive before after study design, we're implementing the countermeasure at some given time period. And so what we do is we measure how many crashes occur during the period prior to implementation. And if we look at reference manuals and best practices, generally the recommendation is that we have at least 3 years of data before the treatment was implemented. Any insights as to why we want to establish a minimum number of years of data for that before period?
Help minimize outliers.
Yeah, so that's a big part of it. As we increase the number of years of data we have available, we're going to have a more reliable estimate of what the long-term safety performance of that site is, right? And so I think we're probably thinking along the same lines here, but when you talk about minimizing the impacts of outliers, what do you mean by that exactly?
Like if 1 year just experiences way more or way less than is typical, the other years should make up for that, statistically speaking, I guess.
Yeah,
Should help
exactly.
bring it back closer to average.
Yeah, so if we think about where we're going to implement safety treatments, it's predominantly going to be at the sites that experience the most crashes, right? And so if we put together a ranked list, as we've done in the network screening examples previously of what sites have experienced the most crashes, we're going to pick sites from the top of that list. And even if we did nothing, it may just so happen that during the preceding year, if we did the ranking just on 1 year of experience, for example, we'd probably see significantly different results than if we averaged over 2 or 3 or 5 years. Now, there's also some literature that suggests that the period shouldn't be overly long. So 10 years might not be a good idea for an analysis time period. Any thoughts as to why that may be the case?
I mean, maybe over a 10-year period, there's other factors that could change, like, land use around the area or traffic volumes or patterns or things of that nature.
Yeah, so there's a few different factors there. So one of them, as you had alluded to, is 10 years is a relatively long time period, and there are a lot of factors that could change. One simple factor that could change is just there may have been something done at that specific site, and what we'll often find is that it's not necessarily easy for us to go back and conduct longitudinal comparisons. So for example, sites look like this in 2021, and those same sites look like this in 2016 or 2011 or whatever the case may be. Now, we can get part of the way there if we look at like Google Earth and some of the historical imagery we can get from there. But generally speaking, if we look at the databases that are maintained by road agencies, they're particularly interested in being able to evaluate in real time or essentially real time how those sites are performing and identifying characteristics of those sites. But they generally aren't designing these systems for the purposes of doing research and going back in time and looking at these differences in sites over time. It's more of a real time and moving forward of trying to forecast where we may see some issues in the future. And so we'll talk about that a little bit more when we get to some of the subsequent methods. But those are, several of the reasons why there are some potential limitations. Now, with that being said, we've conducted a number of studies that have shown that the results of just a simple naive before and after evaluation are very comparable to what we'd see with anything ranging up through an empirical base. And so if we think back to some of the content from 849 and what would tend to give us more reliable estimates, that would include, more years of data, more sites oftentimes. If we've implemented a countermeasure at 5 or 10 sites, we'd tend to see more robust information than if we had done it at just one site, because at that one site, there could be some site-specific factors that would make that treatment more or less effective as a consequence. So if you think about some unusual intersection designs or some circumstances that may exacerbate crash risks, we might not see those same scenarios in other instances. So those are just a few of the big picture concerns here. Now, one important consideration here, so in the preceding diagram, we basically were assuming that crashes were at some level, we implemented the treatment, and then crashes were reduced subsequently. And so a natural question there is, well, how do we know if that treatment was effective? And that's just not just a function of some random fluctuation in the data, or, like we've talked about in 849, just unluckiness on our part from a sampling standpoint. So typically, this would be a good candidate for conducting like a 2-sample test of means, basically, right? So we could look at the average number of crashes pre-installation, we could look at the variability in crashes from year to year, and then we could do the same thing in the after period, and we could conduct students' test or Welch's test, and on that basis, make a determination as to whether or not that treatment appears to be effective. Now, one problem we run into with that approach is crash data, generally speaking, if we look at crashes on a site-specific basis, tend not to follow a normal distribution. They tend to be better approximated by a Poisson distribution. And so I'm trying to remember if we've got into this in 849 yet. I don't know that we have. And so are we all familiar with the Poisson formula and how this works in essence? So we essentially have a long-term rate, and in this case, this would refer to, for example, the number of crashes we'd expect to experience per year at a given site. So lambda is a number of times we'd expect to observe that phenomenon over some given time period. And given that average value, a defining characteristic of the Poisson distribution is that the mean and the variance of that distribution are equal to one another. And we can use this probability density function to determine how likely it is that a site with some given mean number of crashes would experience X crashes per year, where X is any integer essentially. And so if we look at that, as I had alluded to, this is the mean number of crashes per year. That's simply probability. And I believe on the next slide here, this is just showing us an example, which would be common for various types of sites. So on the x-axis here, this is the number of crashes we'd expect to see per year. This is the probability of that site experiencing any number of crashes. And so thinking about this conceptually, then, if we're trying to determine whether or not a treatment is effective, if we know what the mean number of crashes on an annual basis was prior to the implementation, we can use that to basically define this Poisson function, right? And then we would review crash data for some number of years after the treatment has been implemented. And if we think about this in concept, so for this given site, it looks like our average number of crashes is probably somewhere in the range of 3 or so per year. And so on that basis, we can look at how many crashes are experienced after the fact. And if the treatment was effective, we would tend to observe values that are, I guess I'm leading the audience here. Where would our values tend to be observed if the treatment was effective relative to this distribution?
Towards the left, the low end.
Yeah, so it would tend to occur, we'd be interested in the lower tail of this distribution, right? And so this kind of highlights one of the issues we'd run into if we tried using a t-test here, right? Because under a t-test, we'd be assuming that those crashes were normally distributed. And so we'd be basically overlaying a bell curve on top of this, which would be very poorly representative of the lower tail of that distribution, okay? And so that's why it's important. Now, with that being said, I should step back a little bit, because there are some instances where it's perfectly fine to assume your data are normally distributed. And this is an interesting area in the research literature, because oftentimes when we publish papers, we'll make assumptions that the data are Poisson distributed or something similar to that. But depending upon the nature of the data, there are some circumstances where the normal distribution is a reasonable assumption. And if we think back to the central limit theorem, if we're conducting repeated samples over time, eventually this distribution is going to tend towards a normal distribution. And that's going to tend to happen as our number of samples increase, which in this case would mean we either have a very large number of sites, or we have a very large number of years of data as an example, or the other case is that we simply have a very large number of crashes, so on average at a given site or across a group of sites. Because if our mean, instead of being around 3, was in the neighborhood of 20 or 30, what happens to this distribution is it starts to become stretched out. We'll generally still have some positive skew up to a point, but once you get beyond, say, a mean of 20 or 30, it's fairly well close to a normal distribution. And so when we look at things like, let's say, the number of crashes or fatalities in a state or in a county or things of that nature, I would expect from year to year, those would tend to follow a normal distribution. It's when we're looking at individual locations where crashes tend to be relatively rare and random, where we see divergence from those methods, okay? And so in terms of trying to figure out whether or not we've seen a significant reduction in crashes, we could basically go back to the formula on the preceding slide, and using the pre-treatment average here, we could just determine how likely it is that we would experience X, where X is just however many crashes we experienced after the fact. So that number or less, okay? So we'd be focusing then on the leftmost tail of that distribution, which in this case doesn't really look like a tail given how small that mean is. So in this circumstance, it would be very hard for us to demonstrate that there was a significant reduction in crashes just because the mean number of crashes was so small, for example. So we'd either need a large number of sites or a large time period such that we could drill down, and you basically have to see probably an average of between 0 and 1 crashes per year unless that sample is particularly large, okay? And so when we want to evaluate these, there have been some tools that have been developed historically. I guess I'm curious, Jordan, have you seen this before in Dr. Gates's class? Okay. So this is basically showing us, based on confidence limits, how much of a reduction we would need to see in crashes in order for that reduction to be statistically significant. And so basically, each of these lines corresponds to a different confidence interval. And so at higher confidence, keep in mind, as we increase our confidence level, we're being overly conservative. And so we're minimizing the likelihood that we would commit a type 1 error, for example, here. And so in context, what that means, if we look at how this graph is structured, this is basically showing us as the percent change in crashes. In this case, we'd be looking at a percent reduction. So the amount by which we're reducing crashes from that pre-treatment period versus the expected number of crashes we'd expect to see if the treatment hadn't been applied. And so this is basically the average number of crashes during the before period at a site or a group of sites. And then this is the average reduction we'd see in crashes between the before and after period. And so we would be able to conclude that the treatment was effective if one of two general conditions is true. Either we see a very large decrease in crashes, and so as our percent reduction gets larger and larger, we're going to reject whenever we're in this top right area of the graph that you see right here. And so that's going to occur when either we see a large reduction in crashes and or, pardon me, we see a relatively high number of crashes during the before period, because then we'd have more reliability with respect to that estimate, okay? And so for any given site, then we can determine, and so for example, if we only have 5 crashes that occurred during the before period, it's going to be very challenging for us to show a statistically significant reduction. We'd basically have to be on the magnitude of a 35% reduction at 80% confidence, and in the neighborhood of a 90% reduction at 99% confidence, okay? But as we increase the number of years of data or the number of sites in our sample, then you'll see those numbers start to drop relatively quickly, and then they start to level off once we get into these ranges out here, okay? So relatively straightforward, easy graphical, and this is basically just developed by taking the Poisson probability distribution function previously, running through a bunch of hypothetical scenarios and constructing this curve on the basis of different assumed values for lambda and for those corresponding reductions. Make sense? Okay. All right, now back to the limitations that we had started talking about a little bit previously. It's critical in this case, the conclusion we would arrive at the end of the day here, if we reject the null hypothesis, we'd basically be determining that the treatment is what had facilitated that reduction in crashes that we observed. However, a common concern we run into in any type of analysis, but this is a particular problem in safety analysis, or really a wide range of different transportation engineering applications, because we're generally dealing with data that characterizes driver behavior and just the fundamental nature in which we drive. There's a lot of variability and there's a lot of factors that affect that behavior and the occurrence of crashes, or the factors that contribute to those crashes having occurred. And so in this study design, we're basically ignoring all of that information. We're just assuming that it's essentially an apples to apples comparison. All the conditions are exactly the same before the treatment was applied and after the treatment was applied, with the one exception that the treatment exists there where it didn't previously. And if we think about the other things that we're not measuring or accommodating for here, we've already talked about a few of these. But one of the big drivers, the strongest predictor you'll see by far for traffic crashes, is just volume, right? The more volume we have, the more crashes we have. Almost universally, I guess that I should caveat that by saying, as long as we're looking at the same type of facility, so if you're looking at an urban freeway or a 2-lane rural highway or a 4-leg signalized intersection, in any of those instances, if you hold all the other factors constant and you increase the traffic volume, you're going to tend to see an increase in crashes. And we'll get into a little bit of the minutiae in terms of when there's a little bit of variability in terms of the relationship between crashes and traffic, but that's a very strong effect. Now, outside of that, there are other factors that play varying roles depending on the context in which we're conducting these studies. So as one example, weather could potentially play a role. And so this is a challenging one because from an analysis standpoint, it's very difficult. I've been involved in several studies where we've tried to control for the effects of weather. But by and large, it's very difficult to tease out what the substantive effects of weather are on crash occurrence, and that is due to several factors. One of which, if you have either of you worked with weather data at all previously? So the National Weather Service and NOAA, let me see, National Oceanic Atmospheric Administration. I mean, they're the weather folks. And we can get really detailed information at where weather stations are located. Now, do you guys have any sense as to how weather stations are distributed generally in a spatial perspective?
So what are they, like 30 miles apart or something like that?
Yeah, so typically we're in the neighborhood of 25 to 30 miles apart. And so if we're trying to account for weather, it becomes somewhat challenging just because there's limitations to the granularity of the data. Now, we've seen some significant improvements with sensor technology these days, but this would turn into a very big tangent that I'm not going to go down at this point here. But that's a factor that makes things difficult. Now, with that being said, I haven't seen a lot of research that's been definitive in terms of what the weather effects are generally, but there are some types of projects, like we had a study a few years ago for the Michigan DOT where we're trying to assess the potential impacts of different lighting configurations installed on the back of snow plows. And you might be familiar with the green light study we had done. We had also evaluated a collision warning system. And so we were just trying to figure out how well we could predict the number of snowplow involved crashes we'd see on an annual basis. So that'd be a clear case where weather would be a big driver because weather would affect how much those vehicles were on the road, basically, right? But if you're trying to account for the effects of weather on just normal, or I guess non-winter maintenance related crashes, there's just a lot of noise that comes into play there, and that's generally challenging. But with that being said, it could potentially play a role. One that's somewhat benign and we typically don't accommodate given the time scale of our analysis would be changes in the vehicle fleet. But if you think about just things like the introduction of anti-lock brakes as an example, or now we're seeing some in-vehicle systems as we move towards a self-driving vehicle fleet. And so when you've got things like automatic emergency braking and forward collision warning and lane departure warning and so forth and so on, those would definitely start to have a pronounced impact, and that would be a function of how quickly those penetrate into the market. Now, at this point, we're probably not going to see sufficient saturation that those have a very large impact for several years still, although they are becoming, in the case of automatic emergency braking, that's now going to be standard installation, I believe, starting in calendar year 2022 by many of the auto manufacturers. Differences in driver behavior. So this is where we get towards, say, that 10-year time period, we might see some differences. And so if you think about things like the introduction of cell phones in vehicles, if we go back to the late 90s, those were still relatively low levels of saturation, and then that's quickly increased very rapidly. And so if we look at general trends, and you may recall from the first few lectures, we saw very pronounced reductions in crashes, or at least crash rate, for a while. Now we've been in kind of a plateau phase for a while. And it's been speculated that some of that is due to some of the in-vehicle distractions that have been introduced. And there's a few other factors that are potentially at play there as well. But in any case, those may have some influence. Crash reporting practices, this really isn't a concern typically when we're comparing crashes at individual locations. It'd be more of a concern if we were trying to conduct evaluations across states. So if we looked at a state like Michigan, where we legalized recreational marijuana, and we wanted to determine the effects of that as compared to states that had more stringent regulations on marijuana use, the crash reporting practices would play a role there. And then also just general randomness and uncertainty associated with our crash data. And there are ways that we can more intelligently control for some of that variability through some different study designs. But in any case, there are a wide range of different factors that could come into play. But the real big driver here would be just changes in traffic volume, essentially. Okay. And so as an alternative to the before-after study design, particularly if we want to control for some of those factors that may be changing over time, one way that we could do that is to look at the sites where the treatments have been applied and also look at crash data for similar sites that basically serve as a control group, just as we'd see in medical research. So for all the vaccine work that's ongoing right now, you'll have a group that's actually receiving the vaccine, and then you'll have a placebo group, right? And so we basically monitor those two groups, and we can determine whether there are other external factors that are also playing an important role beyond just the treatment that's being applied. Now, in our case, we'd basically be capturing data for comparison sites that were similar in terms of the site characteristics, except for the fact that some of those sites had treatments applied and then some of those didn't. And we'd look at those sites over the same time periods. And by using the control sites, we could basically look at general trends that emerge with respect to some of those unobserved factors that may be influencing crashes over time. Okay. Now, with that being said, just as we have in the naive before-after study design, there are some potential limitations that arise here, although this is a bit more robust. Now, first of all, we're assuming that the other external factors affecting crashes have similar effects in both of those groups. And so if we plot crashes versus traffic volume as an example, we'd expect to see the same general trend across each of those groups of locations. We would look at roadway geometry and traffic control and some of these other factors, and we'd expect to see similar relationships in those instances as well. And so to that end, it's very critical that we select those control sites so that it's as much of an apples to apples comparison as is feasible. And so when we think about trying to match sites, traffic volume is going to be a big one here. And I'm trying to think, I know we had an example recently. So there was a study that was done in Iowa that basically resulted in a lot of counties removing stop signs on the very rural farm road network, essentially. So you've got cases where you've got farm equipment and you're trying to get corn to and from market, for example. And so very high traffic by equipment and very low traffic generally at these sites. So, you might see a handful of vehicles per day at a lot of these intersections. And so there was significant concern as to whether the stop signs were warranted there based just on the level of the traffic. And then secondly, trying to maintain those signs over time, given the low level of traffic. And so there was a study that was conducted that basically found that sites that didn't have stop signs tended to experience crash risks that weren't significantly higher than similar sites that did have stop signs. Now, any thoughts as to one of the potential confounds or complexities that would arise in that setting? And I apologize, I realize that was an ambiguous setup, but if we think about that, so you got a bunch of very rural intersections, the vast majority of those have stop signs. And so if you're going to compare those locations and try to do an apples to apples comparison, any concerns that may arise?
Just like how low the volumes are be an issue. It's really unlikely anyway.
Yeah, so basically almost every one of those sites had stop signs. And if you think about the sites that didn't have stop signs, those would tend to be even lower volume than the sites that did. Okay, so there's your first confound. And so, naturally, if you have even lower volumes, you're going to see lower crashes. Ergo, you may not be able to prove any definitive differences. And then and I forget how this had played out. I don't recall the specifics, whether they had actually removed some signs and then conducted an evaluation, in which case it probably wasn't a random determination in terms of which sites they removed those stop signs from, right? I would assume if they had crashes that had occurred nearby, it's very unlikely you would have pulled those signs specifically. And so there's a wide range of potential confounds that could come into play in that circumstance. In most other circumstances, it's fairly straightforward to try to match sites based upon traffic volume, but there is a bit of nuance. So if we're looking at particularly intersection related studies, we try to match by the volume on both the major road and the minor road. In an ideal world, we'd like to match even further than that, but we often find there are limitations with respect to the fidelity of data we have available. Does anybody have any guess where I'm going with that? So if we just have AADT for each of the roads, that's good, but what would our best case scenario be? And I guess to set this up, oftentimes I've seen a number of empirical studies that have shown that the presence of auxiliary left turn or right turn lanes are associated with more crashes. Why would that be the case? Any ideas? So if we look at how these studies have been developed, we're often using AADT on the major road and AADT on the minor road to predict how many crashes we would expect to see. And then we can basically either develop separate models for locations with and without turn lanes, or we can include the turn lane as a predictor variable in the model to ascertain whether crashes go up or down when that turn lane is present. When do we install turn lanes?
Higher volumes.
Specifically higher turning volumes, right? And what we typically find is when we're doing these large scale safety analyses, we certainly don't have turning movement counts. We're lucky in some cases if we've got AADTs for each of the respective roads. And so consequently, this has been a huge challenge in the research community is without that turning movement data, you're going to see much different safety performance if you see a road where you've got 25% of the traffic turning left versus 5% of the traffic turning left, right? Because those are our highest risk vehicles, generally speaking. I haven't seen this to be as big of a problem with right turn lanes, generally speaking, but that's an important factor that is at least correlated to the volume or a function of volume. Related to that, just cross-sectional characteristics. So if we looked just at sites that had left turn lanes, I guess, and we had varying levels of AADT, that would be a more rigorous way, maybe a better way for us to look at that. But even in that setting, if you have unbalanced volumes either across the approaches in each direction, or you have very high proportions of left turns on one approach versus the other, those are a few of the confounding factors that can come into play. Traffic control devices. So we're about to start a roundabout study next month for MDOT. And in that scenario, we'll be looking to compare the safety performance of roundabouts to different types of intersection control. And so we've got to be careful in those types of evaluations because it's certainly, I would say, not an apples to apples comparison if you're looking at four-way stop control versus signalized intersections as an example, minor road stop control. And so all those different scenarios, you'd see differences in terms of crash occurrence, the general types of conflicts that occur that tend to introduce potential limitations or hurdles to our study design. And then lastly, geographic factors. And so in this case, I guess we've got an interesting paper that was, it was either just accepted for publication at TRB or we have some minor comments to address. But as a part of our statewide speed limit evaluation, we compared differences between sites that had 55 mile per hour speed limits versus those that had the limits increased to 65, for example. We also included variables such as the county or region of the state in which those sites were located. And as a part of that, we saw that in some of the southern areas of the state, we saw speeds that were 3 to 4 miles per hour lower than otherwise. And so in that case, the reason for that wasn't because people drive 3 to 4 miles per hour slower in this part of the state. but it was largely due to the fact that none of the speed limit increase sites had occurred in this area. They were all in the northern part of Michigan, okay? And so that's one very unique example where if your geographic factors are different, we may see some general differences from an analysis standpoint there. So I'm saying even irrespective of whether it's a control site that had stayed at 55 or had been increased to 55 from 55 to 65, there are some potential geographical factors. So maybe in those northern sites, even where the speed limits had not been increased, we might see that speeds drift up a little bit because people just may maintain higher speeds, as an example. Okay. So anyway, this helps to illustrate there's a whole bunch of complexity that can occur between individual sites. And so when we're identifying these control sites, we want to be as rigorous as possible in making that determination, because oftentimes I've seen research studies where they'll just go to the roadway database and, well, let's just include all 2-lane highways as a control group versus, say, the speed limit increase sites. And the nuance and the differences you'll see across 2-lane highways, for example, can vary substantially if you're going through small communities versus very rural areas where there's no development. And so you want to be really careful about I think we often see researchers just kind of throw everything into an analysis or a model and see what sticks, essentially. And so that's one thing we want to be careful of here, is that we're taking care in determining what factors we're trying to include in that evaluation. Okay. And so, I wish I had changed this slide. I have an altered version here. It makes it seem overly pronounced here, but this is just an example. If we looked at this scenario and we looked at a naive before-after study design, our reduction in crashes would be basically if we just drew a line straight across and we compare those before and after trends, right? But in this circumstance, something's changed. Maybe its traffic volumes have gone up substantially. And so at the control site, we may have seen crashes go up by this magnitude. If that happened at the control sites, we would expect that same thing would have happened at our test sites, for example, right? And so consequently, the effectiveness of that treatment then would not be this difference, but it would be this larger difference, okay? It would be a bit bigger challenge if crashes had actually gone down at the control sites, because then we'd be overestimating how effective those treatments are, okay? And so that's the one big advantage we get from this control site evaluation, is it allows for us to control for all those other factors that are affecting crashes. And so if we did a safety evaluation study in 2020 or through 2021, we'd probably see some different trends, because you've probably seen COVID has introduced some reductions in crashes generally, but some increases in severe crashes. And so if we just did a naive before and after study and didn't account for any of those differences, there would be some concerns. Likewise, if we were trying to assess the efficacy of that weakening or the legalization of recreational marijuana, we would potentially see that as a confound if we didn't include control sites, because if we assume that that's led to an increase in crashes, as it has in Colorado and a few other states, failure to control for that could either overstate or understate how effective a specific treatment would be, for example. Okay. Now, the last example we'll talk about today is what's referred to as a cross-sectional or comparative parallel study. And so in this context, we're comparing sites where a treatment has been applied to similar sites where the treatment hasn't been applied. However, for some reason, we may not have access to pre-installation crash data for the treatment group, or just longer periods of historical data for the control group even. And this would be very common when we try to do evaluations of things like, let's say, chevron signs or curve advisory warning signs or things of that nature. Because in those circumstances, and this gets back to one of my prior points, the DOT has a generally good idea of where all of those items would be installed, those assets would be installed on their roadway network. But if you asked when they were installed, they would often have absolutely no idea. And that's been getting better over time, but it's still a significant concern because a lot of times they'll just basically have a vehicle drive through these sections and they'll use AI or whatever the case may be. And that process is largely automated. And so consequently, we know that a sign is there or isn't there at a given site, but we don't really know when that was put into place. And so in those instances, what we typically do is it's as if we're doing just the preceding case, the before after with control, but we're only looking at the after period differences because we have no before period differences, because we simply don't know when that treatment was installed. And that's a real problem because those types of treatments that are installed intermittently tend to occur on rural roads where we also tend to see lower numbers of crashes. So trying to evaluate any types of curve treatments, for example, can be challenging. And so if we think about this one in concept, we don't know that when the treatment was applied, we just know that it exists at one site or one subset of sites, and that it doesn't exist at the others. And so in this case, it's going to be really critical that we again match these sites based upon traffic volume and other factors, because we want to make sure that the only substantive difference is that some of the sites have this treatment and some do not. Okay. And so from there, it's a relatively straightforward means of evaluating the difference between the average of those sites where the treatment hasn't been applied, so the control group, versus the site or sites where they have been applied. Okay. All right. And so continuing on that, a few analytical concerns that we'll talk about in a little bit greater detail. So we talked about changes in crashes due to other external factors. And so that, like I said, could be policy related changes, that could be changes to law, changes in weather, traffic conditions, etc. Regression to the mean is another concern. I'm guessing that Jordan would have seen this before. I don't know if Travis, have you heard the term regression to the mean at all? Okay.
Heard of it, but not experienced.
Okay. And then there are also random data fluctuations, as is going to be true with any sort of random variable in statistical analysis. And then another big concern we'll conclude with is site selection bias. And so we generally try to select the sites that are highest risk for these countermeasures. And so typically that doesn't necessarily give us the most reliable estimate of how effective those treatments are on average, as we'll get to in a minute. Okay. So thinking about some of the factors that have been introduced previously. So volume's an important one. And when we previously, in last week, we talked about calculating crash rates as an example. Okay. And so comparing the relative risk of two sites based upon its corresponding crash rate. Within the context of a before and after study, we may be interested in looking at how crashes have changed over time. And so as a part of that investigation, maybe we've got control data, and so we're able to quantify the effects of changes in volume, for example, or we can calculate and compare crash rates between the before and after period. But one limitation that comes into play there is when we're using crash rates, we're basically just assuming a linear relationship between crashes and volume, right? In actuality, what we often see is that there's a curvilinear relationship, and specifically, we'll see more rapid increases in crashes at lower volumes, and then that'll start to taper off. And that's partially can be due to congestion effects. So as you get into more congested road facilities, just speeds drop and you start to see fewer crashes. And so it's more of a problem in more urbanized areas. We found for rural roads that proportional relationship or the straight line linear assumption is reasonable in a lot of instances. But there are certainly circumstances where that relationship's nonlinear. Okay. And so as a consequence of that, what we may find is that we could either overestimate or underestimate how effective a specific treatment is based upon whatever assumption we're making as it relates to that crash volume relationship. Okay. And so as an alternative to crash rates, we could basically try to estimate an empirical regression equation that would be curvilinear in nature. And so here, instead of a unit change in volume corresponding to whatever the slopes of these lines are, we would instead be assessing the differences between these various points on this curvilinear plot. Does that make sense? Okay. And so if we don't account for that, what happens is, as we see here, so we're assuming a straight line relationship. And if we're in the area of the curve where there's a more rapid increase, we would tend to be underestimating the level of risk at those sites. And then conversely, on the other side, if we assume that straight line relationship, we would have been assuming that we'd see more crashes than we would otherwise. And so as a consequence of that, we may end up either overestimating or underestimating how effective a specific treatment was. And even the direction of these would depend somewhat on the nature of the phenomenon we're investigating. So for example, in cases where we introduce some site-specific treatment, we expect that crashes would go down, and we tend to select those sites for that treatment at a high point in the cycle. In contrast, if we're looking at the speed limit increase example, we tend to select sites that have a relatively low crash experience because we're concerned that those speed limits may increase crashes, and those issues could be exacerbated by any of these volume effects that come into play here as well. Okay, so it's a very complex series of relationships that kind of underlie the crash generation process, basically. And another aspect that I had alluded to there a little bit as well is the general phenomenon that's known as regression to the mean. And so what that basically means is if you have random, rare, extreme events, and so in this case, if you have a site that experiences a very large number of crashes or a very small number of crashes over time relative to other comparable locations, if we measure those same sites in subsequent years, those values would tend to come down or up as the case may be and be closer to the long-term average, okay? And so that's particularly problematic in our case because if we tend to implement treatments when crashes are at a high point in the cycle, we may overestimate how effective they are. Or in the speed limit example, if we increase speed limits at sites that happen to have a low year in terms of number of crashes, we may actually see significantly more crashes, which we would then use to overstate the effects of that speed limit increase, okay? And so within the context of before and after type studies, we can see very significant differences. And so this is just a typical type of phenomenon we'd see at a site that averages 20 crashes per year. It's going to be very unlikely you'd see 19 or 20 year after year after year. You're going to see significant fluctuation because there's so much randomness and uncertainty involved with this process. And so if we think about when that treatment is implemented, depending upon where we are in this cycle, we may come to markedly different conclusions ultimately, okay? So if we took just 3 years of before period data and 3 years of after period data, we may see a significantly different picture than if we extended that out to 5 years on either side, for example, right? And so that's a concern. Similarly, this kind of reinforces the two general phenomenons that we see previously. So if we look at individual sites over time, the speed limit policy example, so in that case, MDOT tended to select sites for speed limit increases that didn't have a significant crash history. And so if we took sites that just had the fewest number of crashes over 3 years, and then we didn't do anything whatsoever, we'd still see some oscillation back towards that long-term average, right? Likewise, if we took sites that had the highest number of crashes, particularly if that's on a 1 or 2 year basis, we may find that had we done nothing whatsoever, crashes would have started regressing back towards that long-term average over time. And so as a consequence of that, we would tend to either overstate the impacts of a safety treatment or overstate, in this case, how bad the impacts of a speed limit increase would be, as an example, okay? So there are several different contexts in which this comes into play, but it's really true in virtually any type of random variable. So if you look at sports and things like batting average, for example, if someone happens, and if nobody has baseball background, my apologies, but if somebody bats 360 in a given year, odds are the average is going to drop down, closer to 300 or whatever the case may be in subsequent years, all other things being equal. Now, of course, there's some players who will consistently have higher batting averages, and I'll grant you that, but there'll be outliers as an example. And so that same thing comes into play anytime we're dealing with data that are very stochastic and random in nature, and that's a particular concern with crash data. Okay. To reinforce this point a little bit, I thought this was a pretty good demonstration information. So this is from data that I believe were drawn from Norway going back to the 1970s, but the same phenomenon generally holds. And so this is just showing the number of sites that experience between 0 and 9 or more crashes. So these are very rural intersections. And this just shows us in the subsequent year how many crashes were experienced. And so if we would conduct a naive before and after study, we obviously wouldn't expect that those 0 crash sites would experience 0 crashes. We're going to see some increase here. And so we tend to see these fluctuations the closer the values are to the mean. So in this case, you can tell by inspection probably that mean is somewhere between 0.5 and 1 roughly. And so in this case, the sites that experience roughly 1 crash, that's right around the average. And so the long term, that the sites in the subsequent year experienced a very similar number of crashes. Those sites that experienced more crashes, those numbers tended to regress back towards the mean. And likewise, those sites that hadn't experienced any crashes also tended to regress towards that mean. Make sense? And the same situation is true here. Now, in this case, we had a slightly higher mean number of crashes in this case. And so this is looking at crashes per intersection over a 3-year period. So I don't know why they didn't normalize this. So we should be dividing these numbers by 3 to make this an apples to apples comparison. But so in this case, we would basically see that mean, the regression to the mean is going to be more severe again at those lowest and highest volume sites ultimately. Okay. And so that's one of the big concerns we try to address. Now, there are also instances where if you experience a significantly high number of crashes, this becomes less of a concern. So it's really a particular concern when we either have a relatively small time period of data or a relatively small mean number of crashes per year per site. But these are data that come from some intersection, I forget which, in the Detroit area. And these are relatively stable between the periods before and after that, when that treatment had been implemented. And so I think this was averaged across several sites. And so as our sample sizes and or means get larger, this becomes less of a concern. But oftentimes in safety, we're dealing with data that are rare and random. And so that becomes a big concern. And then a related issue that's very difficult to control for. And so we'll start talking about this a little bit more in 849 as well. But we tend to implement safety treatments at sites where we have an existing problem, right? Now, when we're trying to determine how effective that treatment is, we would basically like to have an average estimate of its effectiveness. As it turns out, most of those crash modification factors we see aren't average estimates, because to get an average estimate, we'd randomly select sites at which to install the countermeasure, and then we'd evaluate performance across that random sample of sites. Why don't we apply treatments at random samples of sites?
Because then you might end up doing something at a site that didn't need it and making it worse, or something along that effect.
Yeah, well, your boss would probably fire you in short order, right? If you put a bunch of safety improvements in at just randomly selected sites. And so that's something that's very difficult to draw out, because invariably we're focusing on more so on the upper tail of that distribution of sites, right? And so as a consequence, and this is rarely covered in the literature, and it's probably not that big an issue, because just by the nature, we're typically, those are the only sites we're interested in. So we can probably think of it as a random sample of our high risk sites. And with that caveat, our results are more reliable there. But if you just think about it in concept, we've got sites that have high crash counts in a given year or 2-year period. And then we have sites that have a very high long-term experience over 5 or 10 years. And depending upon how long our time period is and the nature of those sites, there's this overlap of those. And I won't pretend this is to scale necessarily, but this is just for demonstration purposes. these are the sites that we're truly interested in here, but what tends to happen is that we may often get these sites that are basically seem to be higher risk than they actually are based on those short-term counts, okay? And so we'll start talking next week when we come back about the empirical Bayes method and how that basically allows us to take information using our control group of locations and the relative uncertainty and randomness that's built into our process and try to mitigate some of those concerns that relate to regression to the mean and site selection bias, okay? And so I think that's about, oh, so sorry, this just really quickly kind of demonstrates conceptually what's happening here. So depending upon how we determine which sites would be included in our control group, we would end up with markedly different samples if we were looking at just the entire distribution of sites versus just those sites that are significantly above the mean. And so obviously those distributions are different from one another. If we apply the treatment at this larger sample of sites versus at this narrower sample, we're probably going to see significant differences in terms of how effective the treatments are at those respective sites. Okay. And so that wraps up all I have for today.